the outer configuration of beryllium is 2s2, the atomic number 4 configuration of beryllium is 1s2 2s2, outer configuration is 2s2. So, in 2s2 how it will form bonds? So, this is not explained by valence bond theory and Lewis concept, but here the hybridization explain why beryllium forms compounds or beryllium form molecules and boron and carbon. So, hybridization is when the outer atomic orbitals merge with each other to form slightly the orbitals of slightly different energy. So, when the orbitals of slightly hybridization means when different atomic orbitals merge with each other and form the same set of orbitals, that is same number of orbitals with same energy. The electron configuration these elements are in beryllium 1s2 2s2 atomic number 4, boron 1s2 2s2 2px1 and carbon 1s2 2s2 2px1 2py1. So, from this configuration beryllium should be inert, boron monovalent and carbon should form divalent compounds, but they form beryllium difluoride, boron trifluoride and carbon methane, sorry CH4. To explain these, electron configuration is modified and electrons in valence shell are promoted to vacant orbitals in vacant shells. This process is called promoting the electrons. As you see, the 2s2 electron from beryllium is promoted to 2px1 orbital of 2px1 empty orbital of beryllium, that is the formation of a single electron in two unpaired electron in beryllium and the formation of beryllium difluoride. Likewise, boron, the 2s2 electron from boron, one electron from 2s2 is promoted to p orbital, p empty orbital, and so there is a formation of 3 unpaired electrons in boron and the shape is a boron trifluoride is formed. And again in carbon, the 1 electron from 2s2 is promoted to 2pz orbital of carbon, and there are 4 unpaired electrons. So, we can count for that methane CH4. So, to explain this electron configuration is modified and electrons in valence shell are promoted to vacant orbitals in vacant shell. The process is called promoting the electrons. So, to explain the no need of energy to promote an electron and identical nature of all the bond formed in a molecule, we have a concept of hybridization. So, hybridization is you can say that the word taken from hybrid, which means mixing of different characters. So, here, so when different orbitals are intermixed with each other to form same set of orbitals having same energy. So, different set of orbitals with slightly different energy, they intermix with each other to form same set of orbital of equal energy or degenerate energy. This is called hybridization. So, hybridization is defined as the phenomenon of intermixing of orbitals of slightly different energy so as to redistribute the energies and give rise to a new set of orbitals of equal energy and shape. So, the hybridization is intermixing of orbitals of slightly different energies and formation of orbitals of equivalent energy. So, they redistribute their energy and give rise to a new set of orbitals of equivalent energy and shape. The new orbital formed are called hybrid or hybridized orbitals. New orbital is called hybrid or hybridized orbital. Characteristics of hybridization. Hybridization takes place between the atomic orbitals of same atom having approximately equal energy. So, hybridization takes place between atomic orbital of same atoms having approximately equal energy or slightly different energy. Hybridization takes place between half filled as well as completely filled orbitals, that is valence orbitals are involved in hybridization. They may be half filled or completely filled. Number of hybrid orbitals formed is equal to number of orbitals that get hybridized. So, how many orbitals are formed after hybridization? The number is equal to how many orbitals are hybridized, that is the number of hybrid orbital formed is equal to number of orbitals that get hybridized. The number of orbital is equal to how many orbitals are intermixing with each other. Hybrid orbitals are always equivalent in energy and shape. Hybrid orbitals are always equal in energy and shape, that is when they hybridize. So, the energy is redistributed and the energy is same for all the orbitals. The hybrid orbitals are directed in space in some preferred directions. So, there is the orbitals are directed in space in some preferred direction, or you can say, so when the energy is redistributed and the electrons are equally divided. So, the electron repel each other and the electron after repelling. So, there is a formation of a new shape. All the orbital of a valence shell may or may not take part in hybridization. So, all the orbital, it is not necessary that all the orbital may take part in hybridization. Some orbital might not take part in hybridization. Types of hybridization. Hybridization is of different types depending upon the nature and number of orbitals taking part in hybridization. For example, hybridization involving s and p orbitals. These are of three types: mixing atomic orbital and hybridization. According to mixing atomic orbital, the hybridization is sp3 when 1s and 3p orbitals are hybridizing with each other. So, there is a 1s, there is sp3 when 1s and 2p orbitals are hybridizing. So, the hybridization is called sp2 hybridization. When 1s and 1p orbitals are hybridizing, that is intermixing, the hybridization is sp hybridization. So, hybridization is, so how many orbital are intermixing? So, the name is given according to the orbital intermixing. So, first of all is sp3 or tetrahedral hybridization. When 1s and 2 and 3p orbitals of same shell of an atom mix to form 4 equivalent orbitals. So, in sp3 hybridization, 1s and 3p orbitals of same shell of an atom mix to form 4 equivalent orbitals. So, the hybridization is sp3 hybridization. The new orbital formed are called sp3 hybridized orbital. So, before hybridization the orbitals were s and p, but after hybridization all the orbitals are equal and are equal energy, and the name is also for of all the orbital is sp3, that all the 4 orbitals are sp3 hybridized orbital. These orbitals are directed towards the corners or 4 corners of a regular tetrahedron, making an angle of 109.28 with one another. This is also called tetrahedral hybridization because when 4 orbitals they equal repel each other and form tetrahedral shape. So, these orbitals are directed towards 4 corners of a regular tetrahedron, making an angle of 109.28 with one another. So, each sp3 hybrid orbital has 25% s character and 75% p character. That is, here the picture shown is where 1s and 3p orbitals are shown, and after hybridization the shape below is that all orbitals are equally repelled and they form tetrahedral shape with angle 109.28. So, each sp3 hybrid orbital has 25% s character, that is 1/4 is s character. So, as there are 4 orbital 1s and 3p. So, in 4 orbital one part is of s orbital. So, s orbital has 25% s character and p character of sp3 orbital is 75%. So, each of the 4 orbital has 25% S character and 75% P character, and the shape is tetrahedral and angle is 109.28. So, sp3 hybrid orbital in methane, the picture shown is methane is shown. In carbon, the 1s electron, 1 electron from 2s is promoted to p orbital, and 4 orbital intermix with each other, 1s and 3p. They intermix with each other and form 4 orbital of equal energy, that is a degenerate energy. These are called hybridized orbital. Each orbital is sp3 hybridized, having 1 electron in each orbital. That is, there are 4 electron before hybridization, 2 electrons were in 2s and 1 in p. But after hybridization, all the orbitals have equal energy and all the electrons are equally distributed, and 4 orbital have 4 electrons, and the 4 hydrogen atom one orbital from 4 hydrogen atom overlap with 4 orbital, 4 sp3 orbitals, and there is formation of methane. So, another picture of methane. So, there are 4 sigma bonds in methane molecule. sp2 or trigonal hybridization, when one s and 2 p orbital of same shell of an atom mix to form 3 equivalent orbitals, the new orbitals formed are called sp2 hybridized orbital. These orbitals are directed toward the 3 corners of a equilateral triangle, making an angle of 120 with one another. So, that is in sp2 hybridization. So, 1s and 2p orbital are intermixing with each other, as there are 3 orbitals intermixing. So, this is called sp2 hybridization. It is also called trigonal hybridization because the angle of between them is 120. The angle is 120. The shape of trigonal planar, bond angle is 120. Example are C2, H4 and boron trifluoride. Each sp2 hybrid orbital has 33.33% S character and 66. That is 1/3 is S character and 2/3 is P character. In this, here 1s and 2p are intermixing with each other. Third orbital of p does not take part in hybridization in sp2. So, 3 sp2 orbitals shown below, they all are sp2 hybridized orbital. The angle between them is 120. When 360 is divided by 3, the angle is 120. So, they orbitals are directed towards triangular shape. In sp2 hybridization, there is a sideways overlapping. The unhybridized orbital overlap with each other. In picture, the unhybridized orbital is shown. It shows sideways overlapping and form pi bond. Okay. So, there are 5 sigma bond, 4 with hydrogen and 1 pi bond in carbon. So, S and P bonds in ethylene. So, the picture shows that there are 2 lobes of pi bonds. One is above the internuclear axis and another lobe is below the internuclear axis. sp or linear hybridization, when 1s and 1p orbitals of same shell of an atom mix to form 2 equivalent orbitals. So, this hybridization is called sp hybridization, or it is called also called linear hybridization because the angle is 120 and they form linear shape. The new orbital formed are called sp hybrid orbital. These orbitals are oppositely directed away from each other at an angle of 180. sp or linear hybridization shape is linear, bond angle is 180. Examples are C2H2 BeCl2. So, each sp hybrid orbital has 50% S character and 50% P character. So, example of C2H2 is shown in this example. 1s and one p orbital is hybridizing or intermixing with each other, and the formation of sp hybridization. So there is a linear shape. So two sp lobes are directed away from each other, and as there are only two lobes, so the angle is 180 degree. So here is example of acetylene sp hybridization. So there are two sideways overlapping, as there are two unhybridized orbital which overlap with each other sideways. So there are two types of overlapping, that is sigma bond is shown in between at internuclear axis, and above and below is a pi bond. So there are two types of pi bonds, sorry.